Let's explore how to find the minimal polynomial and inverse of a matrix without computing eigenvalues. We're given that a cubed minus 5a squared plus 8a minus 4I equals 0, and we need to find the minimal polynomial and the inverse. First, let's understand what this matrix equation tells us. This equation shows that matrix A satisfies a cubic polynomial equation. We can write this as P of A equals 0, where P of x is the polynomial x cubed minus 5x squared plus 8x minus 4. This means the polynomial annihilates matrix A, so it's an annihilating polynomial. Now let's find the minimal polynomial of A. The minimal polynomial is the monic polynomial of smallest degree that annihilates A, and it must divide any other annihilating polynomial. Our first step is to factor the given polynomial. Let's factor x cubed minus 5x squared plus 8x minus 4. Let's try x equals 1 as a potential root. Substituting x equals 1 to 1 minus 5 plus 8 minus 4 equals 0, so x equals 1 is indeed a root. Since x equals 1 is a root, we can factor out x minus 1. Dividing by x minus 1, we get x cubed minus 5x squared plus 8x minus 4 equals x minus 1 times x squared minus 4x plus 4. The quadratic factors as x minus 2 squared. So our complete factorization is x minus 1 times x minus 2 squared. The possible minimal polynomials are divisors of this, either x minus 1 times x minus 2, or just x minus 1, or x minus 2 or x minus 2 squared. Now we need to determine which divisor is actually the minimal polynomial. We check if any lower degree polynomials annihilate a. If a minus I equals 0, then the minimal polynomial would be x minus 1. If a minus 2i equals 0, then the minimal polynomial would be x minus 2. Since a is 3 by 3, and we have two distinct linear factors, the minimal polynomial must include both. The minimal polynomial must be either x minus 1 times x minus 2, or the full cubic. That is, either x minus 1 times x minus 2, or x minus 1 times x minus 2 squared. For a general 3 by 3 matrix with this annihilating polynomial, the most likely minimal polynomial is x minus 1 times x minus 2 squared, which equals x cubed minus 5x squared, plus 8x minus 4. Now let's find the inverse of A using our matrix equation. We start with our original equation, a cubed minus 5, a squared, plus 8, a minus 4I equals 0. Let's rearrange this to isolate the identity matrix term. Moving 4i to the right side gives us a cubed minus 5, a squared, plus 8a equals 4i. Now we factor out a from the left side. This gives us a times the quantity a squared minus 5a plus 8, I equals 4i. Dividing both sides by 4, we get a times 1/4 of a squared minus 5a plus 8i equals the identity matrix. Therefore, the inverse of a is 1/4 times a squared minus 5a plus 8i. Let's verify this makes sense. If we multiply a times our proposed inverse, we get 1/4 times a cubed minus 5a squared plus 8a, which equals 1/4 times 4i, which equals I, confirming our answer. Let's summarize our complete solution. Part A, the minimal polynomial is x cubed minus 5x squared plus 8x minus 4, which factors as x minus 1 times x minus 2 squared. Part B, the inverse matrix is 1/4 times a squared minus 5a plus 8i. The key insight is that we can use the given matrix equation to find both the minimal polynomial and the inverse without ever computing individual matrix entries or eigenvalues.